First among the benefits of SQL injection attacks certainly is the stealth. It's highly unlikely that an attack against SQL backend through a web front end, whether it's web apps, web servers, some combination of those, is going to get detected. And this gets down to how websites are administered. Oftentimes, the database team and the web team are actually different folks with different levels of expertise and different knowledge. This actually helps us as ethical hackers because the web front end is probably not looking for SQL injection attacks. The database backend is probably assuming that the web front end is never going to present an attack medium or some type of attack surface. And therefore, this kind of disjoint between the two fairly important components, which play together in almost all e-commerce sites, allows us to slip through those cracks and maybe send the occasional database command that the web server doesn't check and that the database trusts. This combination of not checking and trusting is what allows us to send these arbitrary commands in and actually have them run. How they work is pretty straightforward. It's oftentimes the case that web applications don't check parameters when you type them into a field. When the user types some code into a field or some information into a field, the web applications very often do not check those fields before they're sent to the backend database, assuming that the backend database will have some security and check those fields. And at the same time, the web applications are typically trusted by the database servers on the back end, as well as the web servers. The web servers are typically trusted by the database servers on the back end, and the web servers do not check the parameters or code before it's passed to the SQL server as well. Oftentimes as well, there are web server code bugs or vulnerabilities where certain parameters are not checked by web servers or certain types of fields are not checked by web servers before they passed to a SQL server, and the SQL server may be expecting, rather, the code to be sanitized or checked before it gets to the SQL server. In addition, because web servers and web applications typically are trusted, and because they may need to run a variety of different commands in a variety of different contexts, usually that connection between the web server and the SQL server is an elevated context, security context, meaning it can run a lot of different stuff. Even if Joe user, who's not typically authorized to do anything except see his own information, if he accesses the web app and then it accesses the web server can't just access the SQL server as Joe, because it has to access it as well for Mary and for Bob and for Carol. And so oftentimes, not universally, but oftentimes, this connection is actually in a highly privileged state. That allows us as an attacker potentially to compromise the server by sending code that maybe Joe shouldn't be able to execute, but the web server itself or some privileged user on the web server could execute. Where might you want to inject SQL code? Well, really, the easiest is either to inject it into a URL if the database and the web front end are using URL parameters or path changes to access different data, or if the web front end actually presents form fields like these here, email address, username, password, and so forth. Oftentimes injecting SQL code into those fields will result in the SQL server on the back end executing those codes verbatim, not just within the context of whoever you're supposed to be, but within the context of the web server itself. And the best way to show this is actually as an example. So for the first example, consider a web page that actually prompts you with enter your login ID and password. Okay, very, very common, login ID and password. And those fields are actually associated with the variables $login ID and $password. Cool. So the web page expects you to type in something like this, mikedan@example.com and password XYZZY. Cool. And what happens on the back end is the web server is going to craft up the SQL statement that you see here, select login ID, full name from the member database, or the member table actually, where login ID equals the login ID that I typed in within single quotes, and password equals the password that I typed in within single quotes. If the passwords match and there's a login ID, a valid ID in that members table, we're going to get a result back to the web server that says, oh, this is Mike's login ID and full name. If that doesn't all match, then we get an error. Oh, look, there, it's either a wrong login ID name or wrong password. Very, very common, very, very straightforward type of form. See it every day, right? Well, what if we want to ethically hack this and see if it's vulnerable to SQL injection? So instead of typing in my password, my typical password, I'm going to type in my login ID, mikedan@example.com, and I'm going to type in a password of whatever, doesn't really matter. I typed in ABC here, single quote, or 1 equals 1. And as you can see, what that does is it changes the SQL statement that's sent to the database to be whatever password or 1 equals 1. It's this password equals password or 1 equals 1 that's the pivotal point here. Because if you think about it, 1 always equals 1. That's a true statement. It's just true in our little universe. 1 always equals 1. And on database servers, they're part of our universe. Therefore, 1 always equals 1 on a database server. So either I type in the correct password for this login ID or 1 equals 1. Either way, I get a successful login for the login ID mikedan@example.com, which means if the system is vulnerable to this type of attack, I can log in with any login ID I want as long as it's a valid login ID using this kind of any password or 1 equals 1, because that's what gets passed back to the database. Kind of nifty, huh? Another possible example here of making an attack, instead of actually typing things on a web form, you may notice that a website uses URL parameters to actually pass information back to the database. So in this example, you're on a commerce database, you type in a product number 12345 and press enter, and the URL that you see as a result that displays the product information is this URL, http prod.example.com, product.aspx, and the parameter is prodnum equals 12345. That's cool. That's fine. That's really, really common. Is this a potential for SQL injection? Absolutely. So instead of just typing in 12345, which is kind of boring and mundane and doesn't get us anywhere with an attack, we type in 12345 semicolon drop table products. What this does is it actually appends the semicolon drop table products to the product number in the URL, or just go into a browser. If you know what the URL is supposed to look like, you go and type this URL directly into the browser. The results are that 2 different commands are sent to the database. The semicolon separates 2 different commands. In this case, we've got one that looks up product 12345. We've got a second command that drops the table products. Drop is the SQL acronym for, or equivalent of, delete. So this will actually delete the product table out of the database. Kind of cool? Kind of crazy? Works well. As a second example here, in case we don't want to actually delete anything, we don't want to trash the database, instead of doing that, how about product number 12345 union, which actually combines 2 different SQL statements, select star meaning everything, from users. What that will do is actually send the command to the database to look up product 12345 and display all fields in the users table from the database. That's kind of useful, don't you think? Displaying the entire users table. And star, again, being all fields, which often includes passwords, email addresses, maybe social, date of birth, really anything that the database has in it.